All right, the witch of Agnesy. I'm not sure how to pronounce her name, but there you have it. A lot of these things, like the cycloid and this, may seem strange if you haven't done these before. This was really part and parcel, or really the meat and potatoes of what mathematicians did for centuries. And not so much anymore in the last 100 years, but if you go back several centuries, this was I don't know how to say it, but really the sort of thing that people were working on. And they may seem like puzzles or quirky little problems, and maybe in a way they were, but they did ultimately um, help make this. Whatever. She's got to sound like a cliche, like this tapestry that is modern mathematics. Okay, so what is this figure? Well, it's actually this one I'm not as familiar with, and I honestly can't remember deriving the parametric equations for the witch. Uh, but that's great because we'll dive into it, like I said, with the cycloid in a natural and intuitive way. And the idea is that we have a circle, and let's put it on the xy coordinate um, system. And since I just glanced at the one in the book, let me. I think I remember the letters. Let me try to use the letters that the book uses, as good as any. Um, and so we have a radius of A, and there's the center of the circle. We'll go up there. And what is the idea? The idea is that, well, there's two ways we can introduce this. One way is we could say, let's pick a point on the circle. Pick a point on the circle. Draw this line. Now, what do I mean this line? Well, I mean the line that starts here and goes through the point that we've chosen. Now, when you read this over in the book, they have no choice, and I would have no choice either if I was writing this. They have to use sort of this old-timey sounding geometry way of formulating a problem. You give all these letters, and you may say like line segment PQ, and so on and so forth. Here I have the advantage I can talk, and I can sort of point to things here, if you will. Now, the idea is that we have a horizontal line. Can't decide if I want to make this dashed or solid, but a horizontal line coming across here, and we want to consider the point where this line that we just drew intersects that particular horizontal point. And then already this seems complicated. It's strange, you know. It's like a long recipe. Do this, do this, do this. And then draw this vertical line. And then draw this horizontal line like this through that point, the original point that we had chosen, the original point that we chose. So we chose a point, we drew a line from the origin to the point that we chose. We observe where that line intersects the horizontal line, which is tangent to the circle at the point, that would be the point, what, 0, 2a? Because radius is a, so let's do it. Then we construct a vertical line through this point and consider where that vertical line intersects the horizontal line, which contains the original point that we chose on the circle. Where'd it go? Sorry. This is a point on the curve. Now, if you read the, I think our book mentioned the fact that which really was a mistranslation from the Latin, and it was supposed to be curve because this would form a curve, not a which. So this is a point on the curve, and every point on the curve is obtained thus. So that's complicated. And I don't think it's even necessarily obvious at first what the curve looks like. You have the advantage because you were reading the book and you couldn't help but notice the beautiful drawing they had made of this curve. But if you think about it, see, if you chose a point down here, really close to the origin, the line would go out here and go really, 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 really far out, right? So we'd be way, way, way out in this direction. And this horizontal line would be really, really, really close to the x-axis. So the point on the curve would be really far that way and really close to the x-axis. What if we had chosen this point right up here? Let's see. If we had chosen this point, then this line would go straight up. That's a little bit odd. Straight up and would intersect here. Then the vertical line would be the y-axis, and this horizontal line would be this line, and the point on the curve would be this dot right here. So I'll leave it to your imagination, but I think you can see that the curve would look something like that. It would have this roughly bell shape. It's not the bell curve, but it would have this rough bell shape. But what we're going to try to do is we're going to try to figure out what on earth is that point. And more specifically, we want to, oh boy, this is a word I hate saying. So I won't say the word I was going to say. We're going to try to find parametric equations which will give us x and y as a function of some parameter. And the first choice, so we are looking for x and y. But the first thing we really want to think about is, what's the parameter going to be? What do we want to think of x and y as a function of? Well, the way I laid out the problem is really a function of this point. You should think about this for a minute. That's very natural. It really is. In fact, that's the definition of this curve. But you immediately have this feeling that maybe this is going to be a complicated way to go about it, because how do you specify a point on a circle? Well, we'd have to look at the equation of the circle. And then how do we know where we were on the circle? I don't know. It seems like, and what I should do is say, pause the video. Well, I'll say it. Pause the video and think about what would be not just a natural parameter, but maybe a parameter that would be easy to work with. So think about it. Okay, now you thought about it? I think that a good place to start would be to consider this angle right here. Now, I may live to regret this. I don't know. But this angle right here. Where should I draw this in? This angle right here. Little arrow there. We'll call theta. You can imagine that if you tell me theta, well, that really will determine that point and then determine the point on the curve. So any point on this curve is determined by an angle written as I've written it right here. Now, what are we going to have to do? Or what are we going to try to do? We're going to say, assume we are given theta. Somebody gives us theta. We have to determine x and y. And again, is that reasonable? Well, yeah. If you told me the angle, someone told you the angle, there's only one line you could draw. Then given that line, you would find that point, vertical line. It would cross in the circle at, one place. Those are the kind of things, we're assuming in one place. Maybe it needs a proof, but I think it's pretty obvious it's one place. Horizontal line. Okay, so the program here is reasonable. This is a reasonable thing to do, but how on earth are we going to do it? Oh boy, how on earth are we going to do it? Well, it would seem as though, given theta, we want to try to figure out what this point is. Yikes. Let's see what we can do. Well, this may be a regrettable move. I don't really know, but what's the equation of this circle? It's x squared plus y squared equals, wait a minute, is this how we write it? I said this was the origin right here. So this is, right here is the center of the circle. Now, what are the coordinates there? 0, comma, what? A. So we have a circle of radius a, but it's centered here. So what is this equation? It's x squared plus y minus a squared equals a squared. Yuck. At any rate, we don't want to give up all hope here. Now we have theta. How can we determine where we are on the circle? Given that, let me go back a little bit. If I'd made a nice drawing and I'd given the drawing to you, except for theta, and then someone came along and told you theta, are you sure you could find this point? Yes. You could even get out a protractor, adjust the angle, draw a straight line. It really is going to chop through that circle at one point. So this is something that we should be able to do. This is the first question. Should you even be able to do it? Once you should be able to do it, then let's see if we have the math skills to do it. Now, how are we going to do that? How are we going to determine, I guess I would like to determine the coordinates of that point right there. And how on earth are we going to do that? Let's see. Well, it occurs to me that we've got a right triangle right here. So this triangle right here. Remember, there's the center of the circle. This is not a radius of the circle right here. Nonetheless, that's a point on the circle. It comes down here like this. There we go, and that is a nice right triangle. Because remember, this is a horizontal line, so it's parallel to the y-axis. This is a vertical line. Okay. Here's theta. It's the same angle right here. So let's see if we can figure out the distance from here to here, which will be the x-coordinates of this point. The x-coordinates, of this point. So what do we want to go with? Sine, cosine, tangent. Cosine of theta. So cosine is adjacent. Let's call this u. So u is this distance from here to here. So cosine of theta is equal to u over, oh no, catastrophe. We don't know what this hypotenuse is. So I take back the whole cosine business. Let's try, what do you think? Sine? Tangent. So tangent of theta. Oh no, except we don't know what this is, do we? We don't know what this is. So let's call this v. So tangent of theta is equal to what? V over u. Well, we've got two unknowns. Where is this leading us? Something maybe should come to mind when you see this. Tangent in here. Tangent in here. Think about it for a minute. You pause the video, click. Think. This reminds me of slope. What is tangent? Opposite over adjacent. So what is the relationship between slope and the angle which is made between any line and the x-axis? Do you remember what it is? Hey, real quick, let me make a quick, see if we can see over here. Quick drawing over here. XY coordinate system. We have some generic line crossing through here. There's an angle theta. There's the relationship between the slope of that line and that angle. And what is that relationship? Well, tangent of theta is equal to this, let's say A and there's B. So tangent is opposite over adjacent. Well, that's rise over the run. So the slope of a line is equal to tangent of the angle it subtends with respect to the x-axis. So this is making me think of slope of the line. Well, that's exactly what it is. So this is the slope of the line. Well, then I can write the equation of this line. As a matter of fact, since it goes to the origin, the equation of this line right here, its equation is y equal to mx, but the slope is tangent of that angle. So tangent, of that angle times x. Now, why is that of any use? Well, this point right here is on this line, but it's also on the circle. So that means this point right here is a solution to y equals tangent of, my computer just made a funny noise again. Oh well, at any rate, tangent of theta times x, and it's also a solution for x squared plus y minus a squared equals a squared. Now, what does this look like? your old friend, two equations and two unknowns. It's not a very friendly looking two equations and two unknowns. So we were mandated to take a deep breath before we dive into this. This looks maybe set up for substitution. So let's try that. But before we do substitution, maybe we should try to simplify this a little bit. Let's give that a shot. So x squared plus y squared minus 2ay plus a squared equals a squared. At least the a squareds cancel each other out. Let me just do the magic of the whiteboard here. We'll cross that out like this, and that equals 0. This is not a very pleasant looking equation. I want to make a substitution. Now the question is, I could substitute this in for y here, or we could solve this for x and substitute it in there. I don't really like the look of either one. But I guess if I had to, let's solve this for x, and then we make this one substitution right here. So let's go ahead and do that. From this, we get x is equal to, we'll divide both sides by tangent, so we'll get cotangent y, and that'll go down in here for x squared. So we'll get cotangent, oops, sorry about that. Is that still visible? Yeah, cotangent squared of theta. So x is equal to this, so we square this. Y squared. I don't know if I really need here. I'll put the y squared out in front like that. Y squared plus y squared minus 2ay equals 0. And now we can solve for y. Now once I get y, what will we have? We'll have the y coordinate of this point as a function of theta. And then hopefully we can do some sort of back substitution and get x as a function of theta. Then once we get this, remember we're still going after this point, but this seems like the first natural place to go. We want to solve that for y. Oh no, it's a quadratic equation. It's a quadratic equation really in theta, because given theta, that makes this a constant. A was given, okay? So, but how do we want to go about solving this? Let's see, is this visible over here? Yeah, let's take this right here and factor out the y squared. So we'll get cotangent squared theta plus 1. Y squared minus 2ay equals 0. Now right away, remember I think I had mentioned Wednesday that, and this is a case where I'm not practicing what I preach. You'd think, since I'm in my own house, that I would have a nice, amazing, beautiful, wonderful trig table posted up on the wall, but unfortunately I don't right now. This looks like something we could use an identity for, so maybe you should pause the video again and think about that. I'm not sure. Like I said, there's a lot of identities I remember. There's some I'm sort of aware of their existence, and some I've just plain old forgotten. But we'll just pause on it for a second. Let's factor y out. If we factor y out, what are we left with? We're left with this cotangent squared theta plus 1, y minus 2a, and that equals 0. So either y equals 0. Now, if you look at the picture, I think we can throw that solution out. I mean, the way I've drawn the picture, we absolutely can throw the solution out. Maybe we want to keep in mind, maybe it's theta is pi over 2, but let's just say that cotangent squared of theta plus 1, so either y is equal to 0 or all this business here, minus 2a is equal to 0. Let's solve this for y. So we'll add 2a to both sides, and then we'll divide both sides by this, so we'll get y is equal to 2a divided by cotangent squared theta plus 1. Now, if this was really, really easy, I guess the book wouldn't have really a whole page devoted to this. And obviously, it's introduced as a fairly challenging topic. So that's kind of a fairly nasty looking yuck. I don't like that. This is a moment where I really want to go back and double check on my work. I hope you've been pausing this video, pause, and checking to see that I've made any errors, or that I haven't made any errors, or if I have made errors, say something about it. Let's go back and find x here was x right here. Ooh, geez. Cotangent theta times y. What is y? Y is 2a divided by cotangent squared theta plus 1. Well, there's x and there's y. But that's not ultimately what we're looking for. We're ultimately looking for this point right here. Now, something just occurs to me that maybe I didn't need both x and y. This only occurs to me right now. Because as a matter of fact, once I know the y coordinate here, I will know the y coordinate here. Hey, that's actually not too bad. So I guess I know the y coordinate here. Look, the y coordinate there is the y coordinate there. So let's make it. Let me write this down so we don't forget this. Okay. So y as a function of theta is this right here, 2a divided by cotangent squared theta plus 1. Now, we certainly want to try to simplify that. It may not be possible, maybe it is. The only thing I can think offhand is use a trig identity, which looks quasi-hopeful, right? You have that whole series of identities, sine squared plus cosine squared equals 1. Hey, quick look, let's see, can you see over here? If you have sine squared plus cosine squared equals 1, let's say we divide both sides by cosine squared. If you divide both sides by cosine squared, you get sine squared divided by cosine squared, which is tangent squared plus 1 equals what? Equals, what's the reciprocal of cosine? Secant. So secant squared. And that's the sort of thing. Oh, hey, well, let's just go ahead and do it. What if I divided, let's divide both sides by sine. Divide both sides by sine. What do you get? 1 plus, what's cosine divided by sine? Cotangent squared equals, what's the reciprocal of sine? 1 divided by sine is cosecant squared. Well, there's an identity, and that's kind of nice. And I think I'll take it. So 1 plus cotangent squared is equal to cosecant squared. So cosecant squared. Oh, but that's not bad. Because look, we've got cosecant in the denominator. So what's the reciprocal of cosecant? Well, sine. So this is sine squared. So in fact, this is 2a sine squared theta. And I think we can live with that. I think that's sort of nice. That's really nice. That feels good, actually. So sine squared theta. Sine squared theta. There's sine squared theta. In fact, that's the parametric equation for y, where the parameter is theta. Now what about x? You know what? This video's gone on long enough. Let me give you the outline that I think you should follow for x, and you try it, and then we'll go over it Wednesday in class. We know the equation of this line right here. Oh, maybe I'll finish it off. I don't know. Maybe let's see. We know the equation of this line. Now, what is the equation of this line? I think I wrote it down right here. I think we can figure out where it crosses here, because where it crosses here, it has to also be this point is a solution for this equation, but also for this horizontal line. What's the equation of this horizontal line? Y equals what? 2a. So let's set those equal to each other. So we get 2a is equal to tangent theta of x. Oh, this maybe is not too bad. Gosh. Let's see. Well, I don't know. Maybe I speak too soon. Well, x is equal to, let's divide both sides by tangent of theta. So 2a cotangent of theta, and that's the x coordinate. Oh, wait a minute. That's the x coordinate right there. They're the same. So there's x. There's y. There's x. And here. I don't know. I don't lose track of them. Now, what did I say at the end of the cycloid video? We need to make sure this is reasonable. We can do that, and then we'll call the video a day, or end it. What if theta is 0? What if theta is 0? That's an interesting case if theta is 0, because if theta is 0, we got a problem. If theta is 0, then this line goes out horizontally. It's parallel to this line. It will never intersect that line. So there should be no solution. If I put a 0 in here, sine of 0 is 0. 0 times 2a is 0. So y is 0. Put a 0 in here. What's cotangent of 0? What's cotangent? Cosine over sine. What's sine of 0? 0. Can't divide by 0. No solution. Hey, that'll be my new thing. I think I'll go like, whenever something comes out the way it should come out. What would be another nice, interesting angle? It's not as obvious what the interesting angles are here. Probably 45 degrees is probably an interesting, angle. But let's just do pi over 2. Let's do a 90-degree angle. At pi over 2, we get this point right here. Well, wait. At pi over 2, this line becomes vertical. Where does it cross the circle? Here, at that point right there. Where does it cross this horizontal line? Right there. Then we have this vertical line. And where does that cross the line through the point? Well, right there. So when theta is pi over 2, we better get this point right here. Now, what is this point right here? This is the point 0, 2a. So let's put pi over 2 into our equations. What's cotangent of pi over 2? Let's see, cotangent of pi over 2. Now, actually, when I think of this, I can't help it, but I'm thinking of cosine over sine. What's sine of pi over 2? 1. What's cosine of pi over 2? 0. So that's 0. So that's 0. So that's 0. So x is 0. Sure enough, that's what it should be. If we put pi over 2 in here, what's sine of pi over 2? 1. What's 1 squared? 1. 2a. Y is 2a. So again, we get this. That doesn't prove this is correct. What actually proves it is this derivation, assuming I didn't make any mistakes. So this and this together are the parametric equations for the witch of Agassi. Yeah, and you know what? You're probably thinking, hey, where's the calculus? Well, we're going to get to it. For example, what would slopes be or areas under curves be, et cetera, et cetera. So we're going to get there. And one thing I should sort of foreshadow is you've taken derivatives of functions of one variable, but can we take derivatives using these parametric equations? And the answer is yes, and it's a little more complicated. So that'll be coming up pretty soon. All right, that's it for this, or now. Bye.